In this section, we're going to learn about acid-base titrations and the resulting pH curves and what information we can gain from those. Really simply, acid-base titrations are simply very controlled acid-base reactions. The general procedure is you measure out a specific amount of an acid or base, and this is the thing that you want to find out more information about. So this is really what you're studying. Typically, the two things you can get from a titration are the concentration of your starting acid or base, and if it's a weak acid or base, you can also find its Ka for the acid or a Kb if it's a weak base. So again, this first solution is what you want to find out about, and we either want the concentration or the Ka or Kb, or both. Then you take a base or an acid. So if you started with an acid, you add a base. If you start with a base, you add an acid. And this solution you know everything about. You know his concentration, you know everything about it, and you're going to carefully add it in small increments. As you add it, you're going to measure the pH. So as you measure that pH, you're going to make a curve that we call a pH curve. So it's just a graph of the pH as you add that acid or base. So let's look at some of these curves and see what information we can get from them. So we can really put them into two categories. We have strong pH curves and we have weak pH curves. In strong pH curves, both the thing you start with and the thing you add are strong acids or bases. In weak pH curves, you start with a weak acid or base and you add a strong thing to it. Strong ones are a little simpler, so let's start by looking at those. So here we see on the left, this is my strong acid, strong base titration, and here on the right is my strong base, strong acid titration. So on the left, we started with a strong acid, which makes sense because my pH starts out very, very low. And as we add base, we see that my pH slowly increases, and then it really shoots up in this region here before it plateaus and ends up at a very high or a very basic pH. So if we think about the process that's happening here, we're adding this acid and base together. And as we add the base, my pH increases. When it shoots up in this region here, what's happened is that we're very, very close to adding so much base that we use up all the acid. And the point at which those two actually cancel out is this point right here called the equivalence point. So the equivalence point is where you've added just enough base that it exactly cancels however many moles of acid that you started with. So in the case of a strong acid, strong base titration, essentially the strong acid we can represent as H3O plus, the strong base as HOH minus, and when we react those together, we just produce a couple water molecules. So if we add exactly the same amount of acid and base, we use up both of those, and all we have is water. And that's why we can see at the equivalence point, my pH is 7. So I have a neutral pH at the equivalence point for strong acid, strong base titrations. For a strong base, strong acid, it's really just the reverse. Because we start with a strong base, we start with a very high pH. As we add the acid, that pH slowly decreases. Right here is where we have very similar amounts. Right at that equivalence point, at that pH of 7, that's where the moles of acid and moles of base exactly cancel out, so I don't have any of either. And then as I continue adding acid, my solution is going to get more and more acidic, and I end up at a very low pH. So really, for a strong acid, strong base titration, the only thing you can get from this is the original concentration of the solution. And I'm going to show us an example of that in just a couple slides. Since strong acids and strong bases don't have a Ka or a Kb, we don't get that information from these curves. So we should just be able to identify where the equivalence point is. For these curves, it's where the pH is equal to 7. It's also sort of halfway up this steep portion of the curve right there. And we'll see how to actually figure out the concentration of the solution based on this. Now let's look at two weak titrations. So here on the left is my weak acid, strong base titration. So I started with a weak acid and added a strong base. And we can see that this black curve, that is my strong acid, strong base titration, and it's just there for comparison purposes. So the weak acid also starts out at an acidic pH, but notice it's a little higher compared to the strong acid. Weaker acid means a higher pH. It has a little bit of a different shape. It has this curve region right in here. And this region right in here is what's called the buffer region. The reason we call it that is because we're actually producing a buffer. So here is my buffer region. If we think about what's happening, we have a weak acid. So in this case, we have acetic acid, HC2, H3O2. We're adding a strong base, sodium hydroxide, and I'm just going to pay attention to the hydroxide piece of that. My acid donates, so I make C2H3O2 minus, and then some water. As we add this hydroxide, we can see that we have this weak acid here, and we're producing some of its conjugate base. And we already know that when you have a mixture of a weak acid and a conjugate base, it produces a buffer. So in this region right here, we've used up some of my weak acid, we've produced some of my conjugate base, so we've actually created a buffer. And that's why this is called the buffer region, not surprisingly. Now, as we continue to add the hydroxide or the strong base, we can see that the pH continues to increase until once again we get this steep portion of the curve, and then as we keep going, it eventually plateaus and we get a pretty basic pH. So just like before, we see that there is an equivalence point, which is the point where the moles of acid is equal to the moles of base. So at this equivalence point, we've used up all of my weak acid, and it's all been, as well as all of the strong base that I've added. Notice that the pH is no longer 7 at the equivalence point. So this black curve again is my strong acid, strong base, so its pH is 7, but the equivalence point for the weak one is a little higher. That's because, as we see in my equation down here, if we use up all of my acid and strong base, all I have left is this conjugate base here. So I'm going to have a basic solution once I reach the equivalence point. And that's why I have this basic pH up here. So although in a strong acid, strong base, your equivalence point is at 7, for a weak acid, strong base, your equivalence point is above 7. It's going to be a basic pH. So the weak acid has strong base titration, has a little more to it. One other thing that we should be aware of, we have this equivalence point, which here it occurs at a volume of 50 milliliters. In a weak acid titration, we're also interested in what's called the half equivalence point. And that's the point that occurs at half the volume of the equivalence point. So if the equivalence point is at 50, the half equivalence point, which I'm going to call HEP here, that's going to occur at 25 milliliters. So you just look at the volume of the equivalence point and you go to half that on your graph. We're really interested in this half equivalence point for weak titrations because, again, keep in mind that in this whole region we have a buffer. That's my buffer region. And we know the pH for a buffer is given by pH is equal to pKa plus log of base over acid. Now at the half equivalence point, I've neutralized half of my original acid, and that's been turned into a conjugate base. So what that means is at the half equivalence point, I have exactly equal amounts of the original weak acid and its conjugate base. So that means this ratio here is going to be equal to just 1. The log of 1 is equal to 0. So this whole piece goes away. So at the half equivalence point, my pH is equal to my pKa. And that means by looking at one of these curves, if I identify the half equivalence point, I can also identify the pKa and thus the Ka of the weak acid. So my weak titrations have 3 points I'm really interested in. First, they have this equivalence point. Then they have that half equivalence point right here. And this whole region right here, which we call the buffer region. So those are the 3 features of the weak curve that we're interested in. The weak base strong acid titration, very, very similar. Because it's starting with a weak base, we start with a basic pH. Again, the black curve, this is a strong base, strong acid titration for comparison. And we can see it starts at a slightly lower pH because it's less basic. This region right here is again called the buffer region because here I have a weak base, NH3. I'm reacting it with a strong acid, which I just call H3O+, because that's what strong acids generate. Bases accept, so we get NH4+, and it leaves H2O. So once again, once we've used up some of my weak base, it produces sum of my conjugate acid here. And so when we have both of those, as we do right in this region, we have a buffer, so that's called the buffer region. We again have the equivalence point, which is where the moles of base I started with are exactly canceled by that acid that I've added. Now notice that, again, the strong titration had a pH of 7, but this time for the weak base strong acid, it is below 7. And the reason for that is very similar as to our last week titration. Once I've used up all of my weak base, I've canceled it by adding the exact amount of strong acid. I don't have any of these left. Instead, all I'm left with is this weak conjugate acid, so I'm going to have an acidic pH at the equivalence point. At the equivalence point, all of my weak base has been converted to conjugate acid, so I'm going to have that acidic pH. So again, we also have that half equivalence point we're interested in. So my equivalence point is at 50, which means my half equivalence point is at 25, so that's my half equivalence point. And just like we had for the weak acid titration, at that point, my pH is equal to my pKa. Now notice, if this is a weak base, what I'm really interested in is a Kb or a pKb. So this pKa is referring to the conjugate acid. So I need to be very, very careful. I can get the pKa of the conjugate thing from this curve, and then I need to remember that my pKa plus my pKb adds up to 14. So I can get out my pKb and Kb, but it's going to take a little extra work compared to the weak acid titration because my pH is always directly related to my pKa. So I'm going to have to subtract from 14 to get my pKb for the original weak base that I started with. So those are the three features of my weak acid or weak base titrations: equivalence point, half equivalence point, and buffer region. So let's look at some types of questions we might be asked about titration curves. So label the following titrations as strong or weak and determine the approximate Ka of the weak acid or Kb for the weak base. So if we look at these, we can at least decide which ones start off with an acid. That's obviously going to be these options right here, A and C. We start out at a low pH, so those are going to be my acids. We can see that this one starts at a pH of around maybe 3, whereas this one starts out at a pH of maybe 1. The other thing is that this one has its equivalence point as a pH of 7, whereas this one's equivalence point we can see is definitely above 7, so maybe more around 8, something like that. So 7's right there, and we can see that it's above that. So that means this one down here is definitely going to be the strong acid, strong base. It starts at a lower pH, and its equivalence point is at 7. Whereas this one up here is going to be the weak acid, strong base. It starts at a higher pH and its equivalence point is above 7, maybe around 8. So those weak acid titrations are always going to have a basic equivalence point. So for the weak acid, we want to determine the Ka. So if my equivalence point here is at about 300, I'm going to go to the half equivalence point, which is about 150, and read off the pH there. So my pH is, I don't know, maybe around 4.5. So my pH at the half equivalence point is 4.5, which means that my pKa is 4.5, because at the half equivalence point, my pH is equal to my pKa. And so if I want the Ka, really simple, I just do 10 to the negative 4.5, and I can punch that guy into my calculator to get the number for that. Over on this side, these are my basic curves. So I can do the same thing where I look at where we start. So we can see the top one has a pH of almost 14, whereas the bottom one has a pH of only about 9. So it looks like this one's my stronger base. The other thing I can do is look at that equivalence point. This one is around 7, whereas this equivalence point, it's probably a little lower. Not really good with this. All right, my equivalence point, which is right around there, should be in the midpoint of that curve, is maybe more around 5. So this one is going to be my strong base, strong base, strong acid, because it starts at a higher pH and it has a neutral equivalence point, whereas this guy down here is going to be my weak base, strong acid. Again, I can tell because it has the lower pH to start with and its equivalence point is less than 7. A weak base titration will always have an acidic equivalence point. I can also get the KB for this weak base. So here my equivalence point is at 200. So I'm going to look at the half equivalence point, which occurs at 100. And I can see that at that half equivalence point, which is where pH is equal to pKa, my pH there is about 8, which means that the pKa is about 8. Now I want a KB, so I need to get the pKb first, which is 14 minus your pKa. So my pKb is about 4. Nope, I can't do math. My pKb is about 6, right? 14 minus 8 gives me 6, which means my KB is going to be equal to 10 to the negative 6. So again, I'm getting those Kas and Kbs by looking at that half equivalence point. All right, let's look at a second example. Consider the titration for 2 weak bases, each titrated with 0.1 molar HCl. Which one's more concentrated? Which solution has a larger Kb? And I want the initial concentration in Kb of each base. Now the first 2 questions I can get just by looking at the curve, don't have to do any math. Which one's more concentrated? To look at that, I just need to figure out which one required more acid to neutralize it. So they're exactly neutralized at the equivalence point. We can see in this first curve, my equivalence point occurs at maybe about 35 milliliters. Whereas in my second curve, my equivalence point occurs at maybe around 55 milliliters. So since this second curve took more acid to neutralize it, that one is going to be more concentrated. So solution B is going to be more concentrated. All right, second question, which solution has a larger Kb? Now we're going to be able to answer that by calculating the Kb, but we actually should be able to answer it without doing any math. And that's because a larger Kb really means which one's a stronger base. If we look at my starting pH, this one, my starting pH was maybe around 8. This one was around 10. So since this one has the larger starting base, larger starting pH, it must be the stronger base, and therefore it's going to have the larger Kb. Now, it's just a coincidence that it was more concentrated and has a larger Kb. One does not necessarily mean the other, but for the concentration, you look at how much volume it took to get to the equivalence point. For the larger Kb, or the stronger base, you look at your initial starting pH. Now let's determine the initial concentration in Kb. So let's start with A. So Kb, we already know how to do that. So we look at the equivalence point, which again was right around 35 milliliters. So the half equivalence point would maybe be right around there, about 17 milliliters. And we know that at that half equivalence point, pH is equal to pKa, which means that my pKa is maybe right around, I don't know, I'll say 5. So we're just estimating on the graph. My pH is about 5 at that half equivalence point. So that gives me my pKa. That means my pKb is going to be 14 minus 5, which is going to be about 9, which means my Kb is going to be 10 to the negative 9. So that's for A. We could do the same thing for B. So for B, our equivalence point occurs at maybe about 55, we said, which means my half equivalence point is right about there, maybe around 27. So if I read off, my pH is equal to the pKa at that half equivalence point. So my pH there is equal to about 8, we'll say. So my pK is 8. That means my pKb is going to be around 6. And so my Kb is going to be around 10 to the negative 6. So Kb, that one's pretty simple. Now let's do the concentration. So just like for our first question, to look at concentration, we looked at the equivalence point. We're going to do the same thing. So let's do A first. At the equivalence point, we had added about 35 milliliters of acid for part A. Now we need to keep in mind that at the equivalence point, the moles of acid and the moles of base are equal. So if I can figure out how many moles of acid I've added, that will tell me how many moles of base I must have started with because of this relationship. So at the equivalence point, I added 35 milliliters of 0.1 molar acid, which means the moles of acid is given by 0.035 liters, so I just turn that into liters, times 0.1 molar HCl, which means that I added 0.0035 moles of acid. That means that I must have also had 0.0035 moles of base to start with, because at the equivalence point, those two moles are equal, and I didn't add any more base. I've had the same amount the whole time, so however much base I had at the equivalence point, that's also how much I had to start with. Well, now that I know the moles of base, I can get the concentration really easily. Concentration is just moles per liter. So I know that I had 0.0035 moles of base, and I originally had 10 milliliters, or 0.010 liters of that, which means that my concentration is 0.35 molar for A. We can do the exact same thing for B. We're going to look at the equivalence point. It looks like that occurred at about 55 milliliters. And again, at that equivalence point, the moles of acid and the moles of base are equal. So I need to figure out the moles of acid, which is just given by my liters, 0.055 liters, times my concentration, 0.100 molar. And that leaves me with 0.0055 moles of acid, which means I also had 0.0055 moles of base, because at the equivalence point, those two pieces are equal. So we can just get the molarity of that base by putting our moles over our liters again, 0.0055 moles over that 0.010 liters, and that's going to give me 0.55 molar for B. And we can see that we were correct with question 1. This guy had a concentration of 0.055 molar, whereas the top one was only 0.35 molar, so B is indeed more concentrated. So for weak titrations, we should be able to get out both the Ka or Kb as well as the concentration. If I had a strong acid, strong base titration, I would do this exact same procedure to get the concentration. Look at the equivalence point, see what volume you have. Use that with the concentration of that thing to figure out your moles. That tells you the moles of the other piece, and then to get concentration, you just put those moles over the original volume of the solution you started with. So stronger, weak titration curves, that part is exactly the same.